In the last lesson, we talked a little bit about radicals, and we introduced this idea of simplifying radicals. And we're specifically working with simplifying square roots right now. So yesterday's property and rule, so the rule was that you cannot have any square root factors in the radicand, which is the number under the radical or the square root symbol. And the rule that we use to make sure that we're following that rule was the product property of square roots, which basically said that you could take a number in the radicand and you could split it apart into separate square roots or separate radicals. Today we're going to look at a couple more simplifying rules that are going to add on to rule 1 from the last lesson. But in order to talk about those rules, we need to talk about another property of radicals, or another thing that you can do with radicals that will not change the answer. So there's also what's called the quotient property of square roots. So the quotient property deals with if you have a fraction in the radicand. So if you had something kind of like this, so generic fraction, we'll use variables, but that whole thing is under the square root symbol, it's part of the radicand. So what that says is that you can rewrite it as the quotient. So remember, quotient means divide. So quotient means divide of the square roots of the numerator and denominator of the fraction. So basically what that's saying is I could take this and I could break it apart so that I'm individually square rooting the numerator and the denominator. So you can go back and forth between that. So if you have a fraction, you could break your fraction apart into individual square roots. So you could go this way with it. You could also go the other way. So if you have two different radicals that you're dividing, you could also put them together into one fraction. So just to show you that that really does work, this is just an example playing with numbers, just so you can see, yeah, that rule does work. It does give the same answer. So I could take something like this. This is an easy one, intentionally easy numbers to work with. So this guy, we know that 16 divided by 4 is the square root of 4, and the square root of 4 is, we know, plus or minus 2. So another way that I could do that is I could take it and I could break it apart into individual square roots. So square root of 16 over square root of 4. Well, the square root of 16 plus or minus 4, square root of 4 plus or minus 2, and 4 divided by 2 is 2. So I get the same answer no matter which of the two ways I do this problem. So that shows you that, hey, it works. So this is the property or the trick that we can use to make sure that we're honoring simplifying square roots rule number 2. And what simplifying square roots rule number 2 says is that you cannot have any fractions in the radicand. No fractions in the radicand. So no perfect square factors in the radicand, that's yesterday's rule, and no fractions in the radicand. So that's where this quotient property immediately comes in handy, because it lets us break apart the fraction so that we no longer have a fraction under the square root symbol. So an example would look something like this. So this has a fraction in the radicand, and that's not allowed according to rule number 2. So I can take our quotient property and I can rewrite it as the square root of 27 over square root of 4. Problem solved. Now I'm not violating the rule. I no longer have a fraction. Now I have two radicands. I have a 27 and I have a 4, but neither of those are a fraction, so I'm no longer violating that rule. But we can't forget about rule number 1 from the last lesson, which is no perfect square factors in the radicand. So once I've solved the I can't have a fraction under the square root symbol problem, now I need to make sure that I don't have any perfect square factors that I can pull out. And I now have two different ones that I have to check. So I need to check both of those because we don't want to violate rule number 1 from the last lesson either. So that means I have a little bit of cleanup to do with these. So I could clean these up a little bit. So square root of 4, that's a perfect square. That's 2. And remember we said when we're simplifying, we assume a positive solution unless it specifically tells you otherwise, or unless you're working with something like solving a quadratic where you know there's 2 answers. So if you're just simplifying, then we don't worry about the negative solution at the time. So square root of 27, that we can break down. So square root of 27, that we can break down into if we do the prime factorization for it, it breaks down into 3 times 3 times 3 is 27. So I can get one perfect square out of there because 3 times 3, that's 9. So if I square root that, I get 3. So I end up with 3 times the square root of 3 over 2. So now I have crossed rule number 2 off the list because I don't have any fractions in my radicand under my square root symbol. And I also do not have any perfect squares that I could pull out. So this would be the fully simplified answer. So that's rule number 2 and how we can use our quotient property to follow that rule. Now there is one other rule while we're talking about fractions. And on this example problem, it intentionally worked out so that we wouldn't have an issue with it, but it doesn't always work out that way. So rule number 3, no radicals in the denominator of a fraction. Okay. So we're actually going to look at this first example to show you what I mean by that. So this first example, the fraction's already been broken apart. So I already have two separate radicals, one on the top and one on the bottom. So I don't have to worry about there being a fraction under the square root sign. But right now I am violating the rule because the denominator has a radical. It has a square root symbol in it, and I am not allowed to have a square root down there. So that means we have to talk about how we're going to deal with that. Now, before we deal with that, there is some simplifying that's going to have to happen in this problem because there's also some perfect square factors in there. And this is a matter of personal preference, but I like to try and simplify as I go because it gives me smaller numbers to work with when I'm working with things. So I'm going to go ahead and do the simplifying that I can do with this first example problem. And we know that 12 breaks down into 2 times 2 times 3. 2 times 2 is 4. That's a perfect square. So we can take this problem and we can rewrite it as the square root of 6y divided by 2 times the square root of 3. So that's why I said I like to simplify as I can go. The top part right now, we can't do any simplifying. So we've still got this problem though. We still got the square root of 3 hanging down here, and we're not allowed to have any radicals in the denominator according to rule number 3. So there is a trick to solve that problem, and it's called rationalizing the denominator because right now the square root of 3, that's an irrational number. If you try to take that square root, it's a non-repeating, never-ending decimal. So by getting that out of the denominator, we're turning the denominator into a rational number. So that's why it's called rationalizing the denominator. So the trick is to multiply both the numerator and denominator of your fraction by the, we're going to say, radical denominator. And I'll tell you what I mean by that. So the radical part of the denominator of the fraction. So that's square root of 3. So the reason why I want to do this is if I multiply square root of 3, well, square root of 3 times square root of 3. So if I put those together, that's really the square root of 3 times 3. Square root of 3 times 3 is 9, which works out to 3. So the square root of 3 times the square root of 3 is 3. So it's going to kind of take care of that square root. But the problem is I can't just multiply the bottom of the fraction without changing the value of the fraction. So if I multiply the bottom of a fraction of something, I have to multiply the top by the same thing. The reason for that, if you have something over itself, so this part, because I'm multiplying square root of 3 over square root of 3, anything over itself is really just 1. So I'm effectively just multiplying this fraction by 1. Multiplying by 1 is not going to change the value. So the trick is to multiply both the numerator and denominator by whatever the radical is in the denominator that you're trying to get rid of. And it's really the same as just multiplying by 1 because anything over itself really equals 1. So I'm not actually changing the value of the fraction because I'm really just multiplying by 1. Now, here's what's going to happen though. We're going to clean this up a little bit. So remember our product property yesterday. So I'm going to kind of put a little example up here. So let's say if I had the square root of 6, I could break that apart into the square root of 2 times the square root of 3. So I could go this way with it. I could also go the other way. So I could take pieces that are separate and put them back together under the same radical symbol. So that rule from yesterday of breaking things apart into their factors, you can go either direction with that rule. So that same rule from yesterday will let me take the 6y times 3 and kind of put it all together under one thing. So 6y times 3 kind of all in one radicand all together. And then on the bottom, well, square root of 3 times square root of 3, that's just going to make 3 because square root of 3 squared. It's basically what you're doing. The square and the square root are going to undo each other. So on the bottom, that's going to leave you with 2 times 3 because that's when you get, this is what you get when you do square root of 3 times itself. So I now am nearly honoring all my rules. I don't have any fractions anywhere in a radicand. So the top, I don't have any fractions under the square root symbol, and I don't have any radicals or square roots in my denominator. So I'm honoring my rule 2 and my rule 3, but now I need to just clean up and do a little bit of simplifying. So if I break this top part down a little bit more, so 6 I can break down into 2 times 3. So I'm going to flip this to the front here. So 3 times 6y breaks down to 2 times 3 or 3 times 2 times y. So that's the 6y. So you can see there's actually a perfect square hiding there that I can pull out. And then 2 times 3 I can clean up and make that 6. So that means that I end up with 3 times the square root of 2y over 6. So at this point, I am honoring all 3 rules so far. I do not have any perfect square factors in the radicand. I do not have any fractions in the radicand. And my denominator does not have any radicals or square roots in it. There is one last thing that you should always do with a fraction, though. This is just a reminder. This is something you've been doing for a while, but you should always check for. Always simplify your fractions when you're all done. So 3 over 6, I can change that into 1 over 2. So that really turns into 1 over 2. So 1 times the square root of 2y is just the square root of 2y. So square root of 2y over 2 if I reduce my fractions. So that would be my final answer. So let's look at one more example. This example is a little bit busier. It's got a little bit more going on, but it's a great one to put in your notes so that you have a couple of examples to look at. So let's look through this one together and see what we can do with it. So first of all, I told you I like to simplify as I go just because it gives me smaller numbers to work with. So I am going to go ahead and I'm going to look at our first rule from yesterday, and I'm going to see what I can do to break the numerator and the denominator down and pull out my perfect square factors. So 68, I can break that down to 2 times 17. It's the prime factorization times A times C times C times C. So there's the top. So we can see there's a couple of perfect squares we're going to be able to pull out of that. And then the bottom, so 27, 3 times 3 times 3 times A. Again, I've got a couple of perfect squares that I can pull out of that. So I'm going to go ahead and simplify the top and the bottom, and then we'll deal with our fraction rules. So the top simplified, so I end up with 2c times all the leftovers, square root of 17ac. On the bottom, I have 3a times the square root of 3. It's going to be the only thing left in there. So this is why I like to simplify as you go. So if I hadn't simplified before I did anything, in order to get that square root out of the denominator, I would have had to multiply both things by 27a squared, which is a pretty big number. With this already simplified, Now the only place where I have a square root is just square root of 3. So rather than multiplying by 27a squared, I can just multiply by the square root of 3, which is much smaller and easier to think about. So that's why I like to try and simplify as much as I can before I go messing with the square root in the denominator. So we said the trick to get rid of that is to multiply the top and the bottom by whatever square root you're trying to get out of the denominator. So square root of 3 in this case. But I have to multiply the top so that I end up actually multiplying by 1. So now we have to do a little bit of cleanup. So square root of 3 times square root of 3 is 3. So on the bottom, I end up with 3 times a times 3, which we'll clean up in just a minute. And on the top, I end up with 2c times 17ac times square root of 3. So now we're going to do a little bit of cleanup and a little bit of putting things together. So first of all, these two parts I could put back together. I'm not going to be able to get any more perfect square factors out of 17 times a times c times 3, but I can at least put those back together so that they're all under the same square root symbol. So 2c times, if I go ahead and multiply together my 17 and my 3, then I get 51. So 51 AC, and then 3 times 3 is 9 for 9A. Now, there is one last thing we have to remember here, and it didn't come up in the last problem because we didn't have any variables outside the radicand, or the radical, the square root symbol. But remember yesterday we were talking about how when we're simplifying, we look at the positive solution. So in order to avoid these guys possibly being negative, I need to put some absolute value symbols around those on my final answer, just to make sure that we are looking at the positive version of the solution. So that would be my final answer. So it looks kind of long and kind of busy, but it's actually not that bad. It's just tracking through our different rules and our different steps. So there you go. Now we have 2 more rules in the mix, so we have a total of 3 rules for simplifying. So rule 1, no perfect squares under the square root symbol. Rule 2, no fractions under the square root symbol. And rule 3, if you have a fraction for your overall answer, you cannot have any square roots in the denominator of that fraction. So what you're going to do today is you're going to practice some problems, kind of like our example problems that we were looking at, that are going to get you using all 3 of our rules to make sure that you're doing okay with our rules so far. So when you're ready, you can go